Let's forget everything you think you know about algebra. The dusty textbooks, the confusing equations, just for a moment. Because what if I told you that algebra isn't really a math subject at all? What if it's a language? And not just any language, but one of the most powerful ones ever created. The one we actually use to describe the very fabric of the universe. Okay, so let's really dive into that idea. Over the next few minutes, we're going to decode the essentials of this language. And this isn't about just solving for x. This is about learning how to read the blueprints of reality itself. We're talking everything from the tiniest particles to the biggest galaxies. Every language has a story, right? A history. And algebra is no different. So to really get a handle on its power, we got to go back and see where it came from. And trust me, its origins might surprise you. So get this, the word algebra itself comes from the Arabic algebra. Now, you might think it means unsolvable homework problem, I get it, but it actually means a restoration or a reunion of broken parts. And when you think about it, that's exactly what we're doing when we solve an equation, isn't it? We're restoring the balance, putting the broken parts back together to make both sides equal. It's actually a pretty beautiful idea. All right, so if we're learning a language, we have to start with the basics. We need the alphabet, and we definitely need a map to find our way around. Well, in algebra, our fundamental map is the number line. This is it. This is our map. It's just a simple line with a center point. We call it the origin, right at 0. Everything to the right of 0 is positive. Everything to the left is negative. And the cool thing is, every single real number you can think of has its own unique, specific address on this line. This is the foundation for, well, everything else we're going to do. And of course, on any map, you need directions. That's where these little symbols, the inequalities symbols, come in. The easiest way to think of them is just left of and right of. So when you see A is less than B, it literally just means A is to the left of B on the number line. Greater than, you guessed it, it's to the right. Here's a great little trick, by the way. The symbol always points to the smaller number. Now, absolute value, this one's simple. It is all about distance. And distance can never, ever be negative, right? You can't walk -3 miles. The absolute value of -4 is just 4, because it's 4 steps away from 0. And the absolute value of +4? Also 4, for the exact same reason. It just strips away the direction and tells you the pure distance. So we can use this to find the distance between any 2 points on our map. Let's say, how far is it from -5 all the way to +7? All you do is subtract one from the other inside those absolute value bars. The distance is 12 units. It's clean, simple, and it's always going to give you a positive number. Okay, so we've got our alphabet, the numbers, and we've got our map. Now it's time to start creating words and phrases. And this is where the real power of this language starts to kick in. Variables, the infamous X. They're basically the nouns and pronouns of algebra. They're just placeholders. So instead of only being able to talk about the number 5, a variable lets us talk about any number. And that lets us write rules and formulas that work for everything, universally. And that is incredibly powerful. And once we have our variables, we can start combining them with numbers and operations to build algebraic expressions. Think of these as the phrases of our new language. Notice, there's no equal sign here. They're just statements, kind of like 5 times some number times some other number. So evaluating an expression is really just a fancy way of saying translating the phrase. Once we know what our variables stand for, let's say x is 3 and y is -1, we just plug them in. Then it's just a matter of following the order of operations. So first we handle the exponent, -1 squared becomes +1. Next up, we do the multiplication. And finally, the subtraction. And there you have it, our expression evaluates to -3. All right, time for some advanced grammar. Exponents are kind of like a special shorthand that lets our language talk about ideas of incredible scale. I mean, from the totally microscopic to the mind-bogglingly cosmic. And it does it with complete ease. So what exactly is an exponent? It's just a more efficient way of writing multiply this number by itself this many times. That's it. So 3 to the 4th power is just a super compact way to write out 3 times 3 times 3 times 3. It saves a whole lot of time and makes our notation way more powerful. And just like any good grammar, exponents have a few rules. First, when you multiply two terms that have the same base, you just add their exponents. Simple. Second, when you raise a power to another power, you multiply them. And finally, that negative exponent might look a little weird, but don't let it fool you. It just means flip it. It flips the term down into the denominator of a fraction. So what's the opposite of squaring something? That would be finding its square root. The square root of 36 is basically just asking the question, what positive number, when I multiply it by itself, gives me 36? And the answer, of course, is 6. Now, here is a subtle but absolutely critical rule you have to remember. The square root of a squared isn't just a, it's the absolute value of a. That's because the square root symbol itself has one main job. It always gives back a non-negative answer. That's just how it's defined. So the square root of -2 squared has to be positive 2. Okay, we've learned the alphabet, we've got the map, we've learned some words and grammar. So what's the payoff? Let's put it all together and see why this language is so dang essential for describing the actual world around us. Take a look at this number. This is the mass of a single proton in kilograms. I mean, it's just an absurdly tiny number. It's incredibly awkward to write, and it's almost impossible to even read properly. And now let's go to the complete other extreme. Here is the mass of our planet. And again, it's just a ridiculously huge number. All those zeros are just sitting there begging for you to make a mistake when you're writing them down. I mean, can you imagine trying to do calculations with numbers like these? It would be a complete nightmare. This is exactly the kind of problem our new language was built to solve. So there has to be a better way to write them, right? And of course, there is. It's called scientific notation, and it uses that awesome power of exponents that we just learned to clean up these messy, monstrous numbers, making them elegant and actually easy to work with. Just look at that difference. It's amazing. That entire string of zeros for the proton's mass gets condensed into 10 to the -27th. And that mountain of a number for Earth's mass, it just becomes 10 to the 24th. We just use the language of algebra, specifically the awesome grammar of exponents, to write the language of the universe in a way we can actually read and understand. Look, we've really just scratched the surface here, but you now have the fundamental tools. You've got the map, you've got the grammar, and you've got the vocabulary. Algebra is so much more than a class. It's a language for description and a tool for understanding. So the only real question left is, what will you use it to describe first?